Hello everyone, my name is Owens. I'm the president of the Purdue IQ-PARC Quantum Game Club. In this presentation, I want to give everyone a brief introduction to quantum computing. We'll start off by doing a brief overview of the field and where we're at. After that, I want to introduce you to the idea of a qubit and how we use vectors in mathematics to understand qubits. Finally, I want to explain what a quantum gate is and how we use quantum gates to manipulate qubit states to perform quantum computation. So first of all, what is quantum computing? Well, it's very likely you've heard one of the many popular science explanations for quantum computing, something along the lines of classical computers have bits, which can be a 0 or 1, while quantum computers have qubits, which can be in a superposition of the 0 and 1, allowing quantum computers to explore many possibilities at once. While this explanation sounds cool, it does very little to actually explain what quantum computing is. The unfortunate reality is that there just is not an easy explanation for what quantum computing does better than classical computers. It's still an open problem in the field, but what we do know is that there are certain problems for which quantum computers can perform much faster than their classical counterparts. It's important to note, though, that there are many problems that we have no reason to believe quantum computers could outperform classical computers in. An example of some of the problems we believe quantum computers are going to be useful at would be something along the lines of large-scale data processing, machine learning, and doing chemical simulations. When thinking about quantum computing, it's important to realize that it really is just an entirely fundamentally new way of processing information. The laws of quantum mechanics allow us to pose computational problems in different ways that sometimes have significant speedups over classical ways. So where are we right now? Well, over the last decade, billions of dollars have been invested by many of the largest tech companies into developing functional quantum computers. In fact, in 2019, Google announced for the first time that their Sycamore quantum processor had been able to perform a computation that would have taken years on a classical supercomputer. The computation they performed had no practical use. However, this was proof that quantum supremacy was real and that we are nearing the point of quantum computers being functionally useful. However, there is still a lot of work to be done before this happens. Current quantum computers are far too noisy and lack the sufficient number of qubits needed to be able to perform the complex calculations we believe they are capable of. So where are we headed? Well, every year there are breakthroughs in the field. The number of usable qubits and the fidelity of quantum operations has rapidly been increasing year over year. It's extremely likely that within this decade we're going to see functional quantum computing systems being built. However, there was tons of work to be done, both on the side of developing quantum computing systems and on the side of developing quantum algorithms. We still really don't understand what brings about quantum advantage, and understanding that will be a significant milestone in the field. Furthermore, there are likely many applications of quantum computers that no one has thought of yet. It's been extremely difficult to develop quantum algorithms without having functional quantum computers to test them on. The end idea here, though, is that within this decade, it is very likely that we're going to see significant achievements both in the development of quantum computers and on the side of algorithmic understanding of quantum computers. Okay, now I want to talk about what a qubit is. A qubit, or a quantum bit, is much like a classical bit in that it can be in the state of 0 or 1. However, what makes qubits unique is that they can be what's called a superposition. And what this means is that before you make a measurement on a qubit, you can think of it as occupying both the 0 and 1 state at the same time. And then when you make a measurement on it, that qubit will collapse into the 0 or 1 state. Another way of thinking about this is that a qubit is completely probabilistic. And then when you perform measurement on it, with some probability, it is going to collapse to a 0 or 1, and your measurement result will only be a 0 or 1. It's important to realize, though, that while there are many superpositions, measurement is an act which will only ever return a single bit. So how can we think about qubits mathematically? Well, you can think about a qubit as a 2x1 vector. Think about the first entry in the vector as representing the zero-ness of the qubit, and the second entry as representing the one-ness of the qubit. This notation right here is called a ket. It's standard notation in quantum mechanics. It's called for representing a vector. These two kets are typically denoted as a 0 and 1 bits in quantum computing. We'll get back to why that is in a second, but just keep these vectors in mind. They're really important. In quantum computing, it's also standard to denote the arbitrary state as psi. So you can see that here. And the values in psi's state vector is being alpha and beta. So a qubit can be any state characterized by this vector, subject to one constraint on the alpha and beta values. That is that the sum of the squares of alpha and beta must be equal to 1. Or in other words, that the length of the vector representing the qubit must be 1. The fact that a qubit can just be thought of as a vector of length 1 lends itself to certain logical geometrical representations. This is called the bloch sphere, and it's a way of visualizing the state of a qubit. You can think of any position on the surface of this sphere as being a valid state a qubit could occupy. We denote the top of the sphere as being the 0 state that we just talked about, and the bottom of the sphere as being the 1 state. It's not important to understand this now, however it's good to keep in mind that there is a very easy geometrical representation of a single qubit state. So what are these alpha and beta values in a state? Well, alpha and beta are related to the probability of measuring classical 1 or 0 bit. They are not the probability, but they somehow represent it. How do they do that? Well, let's say m of q is the act of measurement on a qubit. We can then formally say that the probability that m of q is equal to 0 is equal to alpha squared, and the probability that m of q is equal to 1 is equal to beta squared. This is why I said earlier to think of alpha as representing the 0-ness of the qubit and beta as representing the 1-ness of the qubit, because they both respectively relate to the probability of measuring a 0 and a 1. Measurement is a unique process in quantum computing. It's destructive in that after performing measurement, whatever result you measure then becomes a state of the qubit, meaning that repeated measurements on the qubit will always yield the same value. In other words, if you were to perform a measurement on some arbitrary state with alpha and beta values, these values would be changed post-measurement and lost. So those 0 and 1 bit states that we talked about earlier are denoted as such because they measure as 0 and 1s with 100% probability. Stated more formally, we could say for the 0 bit that the probability of measurement of q equals 0 is equal to 1 squared, and the probability of measurement of q is equal to 1 is equal to 0 squared. Likewise, but opposite for the 1 bit. You can essentially just think of these vectors as representing the classical 0 and 1 bit that you're probably used to. Besides the 0 and 1 state, there are two other states which often show up in quantum circuits: the plus state and the minus state. These states are significant for a couple of reasons. First of all, they are what is known as the equal superposition states. That is, that they measure as 0 and 1 with equal probability. In other words, we can say that the probability that m of q is equal to 0 is equal to the probability that m of q is equal to 1 is equal to 1/2. The other reason that these states are significant is because by only applying 1 or 2 operations, we can turn a qubit into either one of these states. In fact, many quantum algorithms begin by first applying an operation to turn all of their qubits into the plus or minus state. It's really convenient that we can represent a qubit as just a vector of length 1. However, any quantum computer which hopes to perform meaningful computation is going to need more than one qubit. Fortunately, linear algebra provides us a means of extending this idea of state vectors to more than one qubit. In linear algebra, there's an operation called the tensor product. A brief overview of what the tensor product is here. So if we say we want to take the tensor product of these x and y vectors, what you would do is you take the x0, the first entry in the vector on the left, and you multiply it by every entry in the vector on the right, appending them to the newest vector as you go. So you get x0, y0, x0, y1. Then you move into the next entry on the vector on the left, x1, and do the same thing for all the y values. The tensor product is essentially just the operation of multiplying every entry with one vector with every entry in another vector. So let's think about applying this to the 0 and 1 bits that we discussed above. This right here is the ket notation for tensor product. Notice how it's essentially just writing the binary number in a ket. If we were to perform this tensor product operation, it would leave us with this state vector. What this state vector is telling us is that when we perform measurement on both of the qubits, with 100% probability, we are going to measure a 0, 1. Which makes sense because that is the state that they are occupying. So for n qubits, a vector of length 2 to the n is needed to represent them. This new vector is still subject to the same constraints on the old vector. That is, that the sum of all the members of it squared is equal to 1. You can think of each position in this new vector as being related to the probability of measuring an increasing binary number. What I mean by this is that the first entry would be related to the probability of measuring all of the qubits as a 0, and then the next entry would be related to the probability of measuring all the qubits as a 0, except for the last one as a 1, so on and so forth, counting up in binary until you get to the last entry in the vector, which would be related to the probability of measuring all of the qubits as a 1. We can state this more formally by saying that the probability that measurement of Q1 and Q2 is equal to some binary number is going to be equal to that binary number's amplitude or value at that position squared. Okay, now that we understand qubits and how we can represent them, let's talk about classical logic gates. It's likely that we all have some familiarity with how classical computers use gates like and, not, and or to perform classical computation. By cascading these gates together, you can perform any type of classical computation. Quantum computers are much the same. However, in quantum computing, we represent operations on qubits as matrices. More formally, we use what are called unitary matrices. The formal definition of a unitary matrix is that it is a matrix whose complex conjugate is its own inverse. Less formally, though, that fact implies two things about the matrix. First of all, that matrix is going to preserve the length of whatever vector is multiplied by it. This is important because remember, qubits can only be vectors of length 1. The next thing that a unitary matrix implies is that the operation is reversible. This is a fundamental constraint placed on us by quantum mechanics. Over here we have some of the most common quantum gates. You can see how we know this is how we would represent them in a circuit, and this is how you can think about them mathematically. Then the application of this gate onto a qubit is the act of multiplying this matrix with the state vector representing the qubit. So, that being said, before we go any further, I think it's good to do a little brief refresher on how matrix multiplication works. Let's say we have a 2 by 2 matrix, and we're going to multiply it by a vector with length 2. The way we would do that is we take these values in the vector, and we multiply them by each row in the matrix. So, we would take B0 and multiply it by the value on the left in the first row, A00, and we add that to B1 times A01. That gives us our first entry in our new vector. Then we do the same, but with the next row, giving us the second value in our new vector. Before going any further, I think there are a couple things that are really important to note. First of all, that using those gates shown above, it becomes possible to create any classical gate except for one. Because of this, we know that quantum computers are at least as powerful as classical computers, because we could just simulate any classical circuit on a quantum computer. However, the one gate that can't be copied is a gate that you've probably never even thought about before. It's called the fan-out gate. In classical computing, you can just think of this as being the act of copying a bit. This cannot be replicated because quantum states cannot be copied arbitrarily. This is called the no-cloning theorem, and it's a fundamental law of quantum mechanics. However, the reason that this does not prevent us from simulating a classical computer perfectly on a quantum computer is because in order to simulate a classical computer, it would be sufficient to restrict possible qubit states to only the 0 and 1 state. And since those states measure deterministically, then it becomes possible to copy those states. Okay, the first gate I want to talk about is the Polyx gate. The Polyx gate can essentially just be thought of as a classical NOT gate. What it does is it swaps the amplitudes of the 0 and 1 in a qubit state vector. Let's think about applying this to our arbitrary state psi. In ket notation, we will write this as such: x times the ket psi. This gives us the x vector times the alpha beta vector, and we can see the end result is that alpha and beta is swapped. You can think of this as just swapping the probabilities of measuring the qubit as a 0 and 1. So if you were to think about applying this to the classical, or to the quantum 0 and 1 states, they would just become the 1 and 0 states, essentially operating just like a NOT gate. The next gate I want to talk about is the PolyZ gate. The PolyZ gate is a gate which swaps the phase, or the sign, of the one state in a qubit state vector. It doesn't affect the measurement outcomes, but it's important for other things in quantum algorithms. So again, if we apply the Z gate to our arbitrary state psi, we get the Z matrix times the alpha beta vector, and the end result is alpha negative beta. So since the value of these guys squared has not changed, the probabilities have not changed. Another extremely important gate in quantum computing is the Hadamard gate. The Hadamard gate transforms the basis states, or the 0 and 1 qubit states, into the equal superposition states, or the plus and minus states that we discussed earlier. This gate is extremely important in quantum computing. Many algorithms begin by just applying this gate to every qubit. So if we think about applying this Hadamard gate to our 0 and 1 states, we get the Hadamard matrix times those states vectors, and the end result is that the 0 state is transformed into the plus state, while the 1 state is transformed into the minus state. It's important to note, though, that the Hadamard gate is its own inverse. What this means is that if we apply the Hadamard to the plus state, it just returns our state to the 0 state. Likewise, if we apply it to the minus state, our state is returned to the 1 state. What this means is the Hadamard times itself is equal to the identity matrix. The last gate I want to talk about is the C-NOT gate, or the controlled NOT gate. You can think about the controlled NOT gate as being a gate that applies an X gate to a target qubit if the control qubit is a 1. I don't really like this explanation, though, because it implies that this gate is making some kind of measurement on the control qubit. So I think it's actually better to say that what this gate does is swap the amplitudes in the state vector where the control qubit is a 1. What I mean by this is this. Let's say we have our arbitrary state psi1 and psi2 tensored together. So this represents 2 qubits, where psi1 is one of the qubits and psi2 is another one. If we apply our controlled NOT matrix to the state, where psi1 is our control qubit and psi2 is our target qubit, this is our end resulting vector. Notice how these two amplitudes are swapped. That's because these two amplitudes correspond to the amplitudes where psi1 is a 1. Okay, with all that information in mind, let's talk about our first quantum circuit. The way to look at this circuit, and the way to interpret any quantum circuit, is basically reading left to right. We start with our initial states, and as we progress, we just apply gates in the order that we encounter them. So, initially, we initialize all the qubits in this circuit to the 0 state. So our initial state is 0 tensored with 0. And then, at time equals 1, we apply a Hadamard gate onto our first qubit, transforming our state into the plus state tensored with the 0 state. So our new state vector is 1, 0, 1, 0. You may be looking at this and thinking that this is not a vector of length 1, so it couldn't possibly be a qubit state. However, in quantum mechanics, it's quite normal to just neglect normalization on the vector for just ease of representation. However, we would actually have to normalize this so that the length is 1 in order to guarantee that it is a valid qubit state. Okay, after that, we apply the controlled NOT gate to these two qubits, and the end result of that is the swapping of these two amplitudes. This is an extremely important state in quantum computing. It's called the Bell state. Notice how making a measurement on one of the qubits will tell you the state of the other qubit without you needing to measure it. What I mean by this is this. Let's say we perform a measurement on our first qubit, and the result of that measurement is a 1. We know that because the amplitudes here are 0, our qubits collectively cannot occupy the state 1, 0. So they must be occupying the state 1, 1. What that means is that both qubits will be measured as a 1. So we've thus figured out that this qubit will then be measured as a 1 if we perform measurement on it. This is an example of entanglement between two qubits. If you measure one qubit and get a 0 or 1, the other qubit must also measure with the same value. Let's talk about the tensor product again. Let's say we have the tensor product of two arbitrary quantum states, psi1 and psi2. That leaves us with this vector. And let's say we wanted these two qubits to tensor together and give us this Bell state that we've had just formed from our circuit. In order to get that, there are 4 constraints placed on the values within these vectors. That is these here. However, notice that this constraint here implies that either beta 1 or alpha 2 is equal to 0. However, if that were to be true, then either this statement or this statement would have to be equal to 0 as well. What this means is that this vector here cannot be formed from the tensor product of two individual vectors. This is an example of quantum entanglement. Quantum entanglement is the situation when the state vector for multiple qubits cannot be formed from the tensor product of individual qubits. What this means is that we've literally lost the ability to describe these qubits individually. It no longer makes sense to even think of them as being individuals. We can only describe them within relation to other entangled qubits. Alright, with all that in mind, I think it's time to look at our first quantum algorithm. Don't expect you to understand this yet, but this is an example of Grover's algorithm. Grover's algorithm is an algorithm for searching unstructured databases. On a classical computer, if you were searching an unstructured database for an entry, on average you would have to do n over 2 queries to that database to find the value you're looking for, and in the worst case you would have to check all n entries in that database. However, using this quantum circuit right here, we can search an unstructured database with n values in square root of n times. Or in other words, we only have to check square root of n values in that database to find the value we are looking for.
Alright, so what have we learned today? Well, the first thing we know is that quantum computing is on the horizon. That is to say that within the next decade, it's very likely we're going to have quantum computers that can outperform classical computers on significant problems. We also learned that we could use a 2x1 vector of length 1 to represent a qubit. And the entries in this vector relate to the probability of measuring a 0 and 1 when you perform a measurement on the qubit. We then learned that we can use the tensor product to extend this idea of state vectors to multiple qubits. Furthermore, we learned that quantum gates can be thought of as matrices, and the act of applying that gate to a qubit is the act of multiplying that matrix by the qubit state vector. Lastly, we learned that entanglement is defined as a situation where a vector describing multiple qubits cannot be formed from the tensor product of two individual qubit states. Thank you all so much for listening. I hope you enjoyed this presentation. If you have any questions, please leave a comment below and I'll try to answer them. Thank you.